So we'll finish up the sigma algebra of Lebesgue measurable sets now. We left off not with a sigma algebra, but with an algebra. So we're denoting all sets that satisfy the Carathéodory splitting condition, that is, all sets that are measurable, with calligraphy M. And we've shown so far that we have calligraphy M closed under finite unions. And we've also shown, these are good sets, good things happen, that we've got finite additivity on the collection of sets in calligraphy M. So they form a sigma algebra. They form an algebra, and we have finite additivity. We need more than that. In fact, they form a sigma algebra, and we have countable additivity, and that's the next thing to establish. So we're simply taking proposition 5 that said closure under finite unions, and proposition 6 it says finite additivity, and carrying both of those to the countably infinite setting. So we're going to show that we in fact have that the union of a countable collection of measurable sets is measurable in proposition 2.7. That means calligraphy M is closed under countable unions. We know it's closed under complements as described above. It's a sigma algebra. So there's kind of phase 1. Phase 1 talks about what sets are in M. Phase 2 talks about their measures. So proposition 2.7 will give us countable collection of measurable sets is measurable. That is, give us effectively that M is a sigma algebra. Now there's still the question to follow about the measures being what they should. And they are. More of that shortly. First, let's prove proposition 2.7, where we're showing closure under countable unions. So let's take ourselves a countable collection of measurable sets. Let's call them A sub k. K equals 1 to infinity. We're trying to show that, assuming each of those A sub k's is in calligraphy M, then their union is in calligraphy M. So we're trying to show, as always, the Carathéodory splitting condition. Being measurable means satisfying the Carathéodory splitting condition. So we're going to try to show, here's the set we're interested in, the union from k equals 1 to infinity of A sub k. We need to show that for any set of real numbers, capital A, the outer measure of capital A equals the outer measure of capital A intersect this thing, plus the outer measure of A intersect the complement of this thing. We need to show the Carathéodory splitting condition applied to this set, the union of the A sub k's. All right, we've already got finite additivity, so no surprise we'll take a bit of an advantage of that. And we're going to define E sub k to be A sub k set minus the union from I equals 1 to k minus 1 of A sub I. Okay, here's what that is just between you and me. E sub 1 is A sub 1 to get the ball rolling. E sub 2 is A sub 2 minus A sub 1. So E sub 2 is the stuff in A sub 2 that wasn't already present. E sub 3 is A sub 3 set minus the stuff in A1 and A2. So E sub 3 is the stuff in A3 that wasn't already present in some of the earlier A's, and so forth. So this is picking up the new stuff. In particular, it's making these E sub k's disjoint. All right, so we're going to take advantage of finite additivity, required disjointness. So that's part of where we're going with this. All right, so the E sub k's are disjoint. Do this for all natural numbers k. We've got the disjointness also at any stage, and when we pass to the infinite union, the union of the E sub k's is the union of the A sub k's. So they contain the same points. We've just taken the A sub k's and sort of chopped them up into some disjoint parts. The E sub k's consist of pairwise disjoint sets. Every A sub k is measurable, so every E sub k is measurable. So let's go through that. Since each a sub k is measurable, then I know the union from 1 to k minus 1 of the a sub i's are measurable. Proposition 2.5, we know that M is closed under finite unions. We also know M is closed under complements, as we observed earlier. So not only is this set in there, but its complement is in M, in calligraphy M. So if we take a sub k, a member of calligraphy M, and intersect it with this stuff here, the complement of this union, since we're dealing with an algebra, this is also an element of calligraphy M. Notice our use of the finiteness at this stage, because that's all we got. So E sub k being a sub k set minus this union, or if you like, a sub k intersect the complement of the union, set minus is intersecting with the complement by definition. Each of the E sub k's is measurable. Okay, so we got measurability of the E sub k's. We need to establish, as we'll need to establish simply the measurability at this stage. We'll address the measure itself soon in the next result. So to address measurability, let A be a subset of the reals, let N be an arbitrary natural number, define F sub N to be the union from 1 to N of the E sub k's. The E sub k's are disjoint union. So that just gives a name to the union of these things. F sub N is then measurable because each of the E sub k's are measurable. Finite unions of measurable sets are measurable, closed under finite unions. Proposition 2.5 is what that was. That allows us to draw this conclusion. Let's elaborate on that a little bit. Since F sub N equals the union from 1 to N of the E sub k's by definition, this is a subset, if you like, of the union from 1 to infinity. If instead of stopping at N, we took a union from k equals 1 to infinity of the E sub k's, that'd be a bigger set, a set that includes this set. So we'd have F sub N as a subset of that bigger set. Here's that bigger set right here. Well, if F sub N is a subset of this bigger set, when we take complements, kind of like multiplying by -1, then F sub N complement includes the complement of the bigger set. Think about it. Since F sub N, forget the complement, is a subset of this set here, forget the complement, then the complement of F sub N is a superset of the complement of this set. So we can throw monotonicity at it. And we will down below. So if we take the outer measure of set A, that's the outer measure of A intersect F sub N plus the outer measure of A intersect F sub N complement, because F sub N is measurable. F sub N is measurable, is observed up here. Here comes the monotonicity part. We're going to take this F sub N complement right here and do some replacing. We're going to get a smaller set on the right-hand side. Monotonicity says you get an inequality of the outer measures. So what we've done is really just taken the F sub N complement and replaced it with this smaller set. You've replaced it with a smaller set. Outer measure is applied to A intersect F sub N complement versus A intersect the complement of this thing. This is a smaller set. Inequality, outer measure, let's call that asterisk. Remember where we're going. We're trying to show that the union of all of the E sub k's, well, actually we're trying to show the union of all the A sub k's is measurable, but that's the same set as the E sub k's. We're going to show the E sub k's, a union of all the E sub k's is measurable, and that's the same as the union of the A sub k's. So that's how we'll draw the conclusion of measurability of the union of the A sub k's. But what we're looking for here to show measurability is the outer measure of A equals the outer measure of A intersect the union of those E sub k's plus the outer measure of A intersect the complement of the union of those E sub k's. So we're not there yet. This F sub N needs to become a union of all of the E sub k's, an infinite union. All right, proposition 2.6 gave us finite additivity. So sum from 1 to n of the measure of the E sub k's, the F sub n's was defined as a finite union. Here we've got A intersect this finite union. We can write that as a sum. Disjointness, we had the E sub k as disjoint, getting an equality here. We get that equality because we made those E sub k's. We created them in such a way that they would be disjoint. So that's where we're using the disjointness by the way of the E sub k's. And so we got a finite additivity dealt with here simply in terms of what F sub n is, but that gives us a finite sum. And we ain't interested in finite sums, we're interested in infinite sums. Okay, but what we're looking at here then is the start equation, outer measure of A is greater than or equal to this plus that. I like that with an eye towards showing measurability of what we're dealing with. This right here can be replaced with a finite sum. So if we combine these two equations, next slide, we'll have the outer measure of A is greater than or equal to this thing plus that thing. Oops, outer measure of A is greater than or equal to the sum, this thing, plus that thing. I like this because it's the infinite union, and we're looking for things related to the infinite union. Okay, that's a lot of symbols, but that's just some number or the infinity symbol. That's just some number or the infinity symbol. And this is a sum of a finite number of numbers, or possibly infinity symbols. But the sum depends on how big n is. This holds no matter what n is. N was arbitrary upstairs. So if you like, we could take a limit as n approaches infinity of both sides. Well, that's constant. That's constant. A limit of a finite sum is a series, and that limits will preserve inequalities. So we would get the outer measure of A is greater than or equal to, since this held for all n, a sum from k equals 1 to infinity. Blah, blah, blah. Same thing here. Okay, so if you like, we just took limits as n approaches infinity. Same logic. Now, I don't want to see a sum of measures. I want to see a measure of a union. But wait, we related the outer measure of a countable union to the sums of those outer measures. And we did so in countable subadditivity. We said, this looks a little bit backwards from the way we stated it, but we said the outer measure of a union is less than or equal to the sum of the outer measures. Series. So we did deal with a countable collection of sets. So outer measure of the union is less than or equal to the sum of the outer measures. That was subadditivity. Countable subadditivity in all its glory here, because we've got a countable union and a countable sum, a series up there. So countable subadditivity allows us to draw this conclusion. And we're going to use a little set theoretic identity that says the union from k equals 1 to infinity of fixed set A intersected with the E sub k's. Notice the subscript k varies in that union. You can bring the A outside and write that as A intersect this countable union, a set theoretic result. I don't want to get into the details on. So we can make a substitution there. That's what we want to see. We want to see, for the Carat-Theodore splitting condition, A intersect the set of interest plus A intersect the complement of the set of interest. So what we got here is half of the Carat-Theodore splitting condition. For arbitrary set of real numbers A, that's where A came from, the outer measure of A is greater than or equal to the outer measure of A intersect the set of interest plus the outer measure of A intersect the complement of the set of interest. But we can reverse that inequality as commented in note 2.3.A. So we saw it's just subadditivity. It gives you the reversal of the inequality. So we can draw a conclusion of equality. Outer measure of A, reversing this inequality, establishes equality with this quantity here. That means this set here, that's a measurable set. So the union of the E sub k's, the countable union of the E sub k's is measurable. But remember, the countable union of the E sub k's was the same as the countable union of the A sub k's. They are the same sets, just the E sub k's are disjoint chunks that were cut up from the A sub k's. but same sets. So the union, the countable union from 1 to infinity of the a sub k's is also a measurable set. That was the claim. So we started with a collection of measurable sets, countable collection of measurable sets, a sub k, and we showed their countable union is again measurable. We've shown calligraphy M is closed under countable unions. We've shown, as commented, finally, calligraphy M is a sigma algebra. It's the sigma algebra of Lebesgue measurable sets, thus the name of this section. Okay, so just as, let me rehash this again to show you we're doing the same thing over again. Just as in proposition 2.5, we showed that a union of finite collection of measurable sets is measurable, but we didn't address their measure. We did in proposition 2.6 when we showed, ultimately, finite additivity. Well, same thing again, only different. We've shown that a countable union of measurable sets is measurable, so M is closed under countable unions. The next natural question would be, well, is the measure of the union the sum of the measures when they're disjoint? It is. That is, we have countable additivity. So if we take a collection of sets, E sub k, countable collection, k equals 1 to infinity, a subset of calligraphy M, so it's a countable collection of measurable sets, and we require that these a sub k's be pairwise disjoint, so no overlaps between any two of them. And the outer measure of the union is the sum of the outer measures. Countable additivity. So we'll go through the proof of this. As memory serves, I think it's actually surprisingly short. This comes from section 2.5, a quick comment. I don't know why they saved this for 2 sections before they actually present it, because we got everything we need to do it now, and it fits in now with the conversation. So let's prove countable additivity. Then we'll know that the measurable sets are a sigma algebra on which outer measure is countably additive. So we've got the outer measure of an interval is its length. We've got outer measure is translation invariant. We've got outer measure is countably additive. We just don't have outer measure defined on every subset of the real numbers. It's only defined on this collection of sets of real numbers. What do you know is in this collection of set of real numbers so far? Measure zero sets and their complements. So you don't know too much just yet about what is measurable. But at least outer measure is behaving very well on this collection of sets. Let's prove countable additivity. Okay. So jumping ahead a couple of sections, but no loss in material. If I were to edit this book, I'd say, or review this book, I'd say, put this result where it belongs, and it belongs 2 sections back where we are now. So take yourself a countable collection of sets E sub k, which are measurable. Then their union is measurable. We just showed that in proposition 2.7, the previous result we proved. By subadditivity, we know the outer measure of the union is less than or equal to the sum of the outer measures. Outer measure was subadditive all along. That's not good enough. That's why we're going through all of this stuff, but it still holds. It's countably subadditive on this collection of sets, for example. Now, here comes the entrance of the finite additivity. Proposition 2.6 shows we've got finite additivity on the measurable sets. So for any n, we're going to do a limit again, the outer measure of the disjoint union of n of those E sub k's is the sum of the measures. Finite additivity. What we're trying to do is reverse this inequality up here. Monotonicity tells us that the outer measure of this union of all k equals 1 to infinity of all of the E sub k's, the outer measure is greater than or equal to the outer measure of the union of only a finite number of the E sub k's. Right, this is a subset of that, so the outer measures behave in the usual monotone way. Oh, the outer measure of the finite union can be expressed using finite additivity. As we just observed, the outer measure of the finite union is the finite sum, so we get an equality there. There's where we're using explicitly finite additivity. And this holds for all n. Again, this is some number, or the infinity symbol, greater than or equal to, well, this is a number as well, but it changes when n changes. It gets bigger, presumably, when n increases. But no matter what n is, we still have this upper bound given by the left-hand side of the equation. So I can conclude we could replace the n with the infinity and take an infinite sum on the right. If you don't like that, then we can take a limit as n approaches infinity on both sides. Left-hand side doesn't change. It doesn't have any n's in it. Right-hand side becomes a series. Combining star and star star, there's your equality. So under these conditions, we get the outer measure of the disjoint union, countable disjoint union, equals the sum, there it is, equals the sum of the measures, as it ought to be. This isn't surprising. The surprising thing is there's sets of real numbers, or disjoint sets of real numbers that don't behave like this. Those are awfully bad sets. We'll explore that. I think it's in section 2.6 when we look at non-measurable sets. But the result isn't surprising. It's very desirable. And basically tells us we're on the right track for our wish list of properties. So let's build now on our list of measurable functions. We know the outer measure of an interval equals the length of an interval. But what we don't know is whether or not intervals are measurable. So we don't even know that intervals are measurable yet. We soon will. Once we do, then things start to happen. Actually, between the end of this sentence and the end of that sentence, a whole bunch of stuff happens. It's not very complicated. Some tedious details we're going to kind of push to exercises. But we're about to really grow our knowledge of measurable sets. One more time. What do we know is measurable? Sets of measure 0 are measurable. We proved that in the proposition above. And so complements of sets of measure 0 are measurable. All right, so you're stuck with, in a measure theoretic sense, really, really small sets and really, really big sets. That's not going to do. It's certainly not going to do if we're trying to generalize Riemann integration and do so by replacing the length of an interval with the measure of a set, if we can't even measure intervals. Outer measure works on intervals. That doesn't mean intervals are measurable. Doesn't mean they're in calligraphy M. Doesn't mean, that is, they satisfy the Carat-Theodori splitting condition. So to show a measure is interval is to show an interval is measurable, we need to show an arbitrary interval satisfies the Carat-Theodori splitting condition. So that's how we will prove proposition 2.8. So let's show intervals are measurable. We got a bunch of intervals in a sigma algebra. Yeah, that's going to lead to a bunch of stuff. All right. First, we're going to borrow an exercise, exercise 2.11 from the homework assignments. It says, if a sigma algebra of subsets of R contains all intervals of the form a to infinity, then it contains all intervals. Why is that? Well, I know what intervals look like. They only come in, 6 different kinds. Open, closed, closed and unbounded, open and unbounded, and just straight unbounded on both sides. I think there's only 5 types. I can write every interval as a union, intersection, or complements of this kind of interval. That's what the exercise says. So establishing that is it's actually pretty tedious stuff. It's not enlightening, but it is tedious. So it's got that going for it. We'll take that as given. So we know we're in a sigma algebra. So if we can show these types of intervals are in our sigma algebra, that is, if those types of intervals are measurable, then then we'll know all intervals are measurable, and then we'll know a bunch of stuff. So let's take this as given. We only need to show for any real number a that the open interval from a to infinity is in calligraphy m, that is measurable. So we need to apply the Kerr-Theodore splitting condition to this thing. So let a be an arbitrary subset of the real numbers. That's what we will split using this thing and its complement. Going to borrow another exercise, a plausible exercise, but still some details to mop up. Without loss of generality, we're claiming we can assume a, lowercase a, the element, this number here, is not in the arbitrary set, capital A. If that weren't the case, we'd replace a by a set minus this, and nothing changes. All the outer measures are unchanged. This is established in detail in exercise 2.9. So let's accept this without loss of generality claim. If you don't like it, work exercise 2.9. It's plausible, a homework exercise anyhow. So is exercise 2.11. Really, that one's just totally messy. So in the past, I've rarely assigned this as a homework exercise because if memory serves, it's not very deep and it's just tedious. It's necessary. Exercise 2.9 is probably a touch tedious as well, but a little bit deeper in the ideas. All right, so here's what we've got. Set A, an arbitrary subset of the real numbers. Well, not totally arbitrary because we are assuming that lowercase a is not in set capital A. And we got this open interval. So define a sub 1 to be a intersect negative infinity to a. Hey, that's the complement of this interval. And define a sub 2 to be a intersect that interval. So we've taken set A, intersected it with a set of interest, and intersected it with the complement of the set of interest. I know A, the element is not in set A, so we could drop this A over here. When I do the intersection of these two things, I know lowercase a is not in set A by the without loss of generality claim. We'd actually replace that and say this is the same set. Capital A intersect the open interval from negative infinity to A. Yeah, neither side includes a lowercase a, so that's how we can draw the conclusion of equality there. But big picture, we've taken set A and we've cut it with a complement of the set of interest, and we've cut it with a set of interest and produced two sets we're calling A1 and A2. A, the arbitrary set, is A1 union A2. A1 includes everything less than or equal to number A, and A2 includes everything in the set greater than A. So we simply took set A and cut it at real number lowercase a. So we get this union. We know by subadditivity that the measure of the union is less than or equal to the sum of the measures. So the outer measure of A is the outer measure of A1 union A2, which is less than or equal to the sum of the outer measures. Subadditivity, very, very finite subadditivity in this case. Okay. And we want to reverse this inequality. We want to draw a conclusion of equality. And we still have to take advantage of the fact that we're dealing with intervals. Okay, so we're going back to the definition of outer measure here. Let I sub k be a countable open cover of A with bounded open intervals. Okay, if we summed up the lengths and took an nth of those resulting sums, that would be the outer measure of A. So we're going back to the definition of outer measure of A, it looks like. So we're covering A with a bunch of I sub k's. This is an arbitrary covering of set A by bounded open intervals, no constraints on the I sub k's. And guess what? We're going to take the I sub k's and cut them as well. Take I sub k, intersect it with the interval from negative infinity to A, call that I sub k prime. take I sub k and cut it with the interval from a to infinity and call that I sub k double prime. So we've got these intervals and we're cutting them at a. We're throwing the endpoint a out if relevant. That's okay. We didn't need it in terms of covering set A. Remember, element A is not in set capital A without loss of generality. So we've cut all the intervals in half. Well, guess what? Then the I sub k prime covers A1, and the I sub k double primes covers A2. We took set A, cut it at real number, lowercase a. We did this, then we covered it with open intervals and cut all the open intervals at the same place. And did so in such a way that we produce more open intervals. Right? The A is being excluded, so we get nothing but open intervals because outer measure is defined in terms of covering the set with bounded open intervals. So after we've done this intersecting, the I sub k primes and I sub k double primes, because we've thrown out A in both of these, definitely open intervals. An intersection of open intervals is open interval. So the I sub k prime and I sub k double primes are countable open covers with bounded open intervals because the I sub k's were bounded themselves. Also, if you'll add up the lengths of, if you'll consider the length of the I sub k, well, it's the length of the left-hand part plus the length of the right-hand part, because those parts join up at the real number a, where you took the interval and that's where you broke it, creating two open intervals. You actually thumped out the point, the real number a, from those intervals. So you broke them into two pieces, and the possibility we got some empty sets around here probably, but the length of I sub k will be the sums of the lengths of the two pieces you broke it into. So the outer measure of A1 would be less than or equal to the sums of the lengths of the I sub k primes. After all, the outer measure of A1 is the nth of all such sums. So I know the outer measure of A1 is less than or equal to this particular sum. Same thing for A2. The outer measure of A2 is less than or equal to this particular sum for the particular covering I sub k double primes. So we can draw the conclusion that outer measure of A1 plus outer measure of A2 is less than or equal to the sum of the two sums. Hey, but wait, for any value k, I know when I add the length of I sub k prime to the length of I sub k double prime, that just gives a length of I sub k. We just observed that. So we can replace this with a sum from k equals 1 to infinity is what we're dealing with here. We started with a countable open cover. K equals 1 to infinity, the lengths of the I sub k's. So the I sub k's, they started as an arbitrary cover of A with bounded open intervals. Since the I sub k's was an arbitrary cover of set A with bounded open intervals, then if we were to take an infimum of both sides of this inequality, looking at the far left and the far right, we take an nth over all such coverings of A. We've got this as a bound below. So the nth will still be bounded by that below. That is, the outer measure of A will be bounded by that below. So we've got the outer measure of A1 plus the outer measure of A2 less than or equal to the outer measure of A. We've got that inequality reversed up here. That was easy. That was a subadditivity. It's also contained in note 2.3.A, I think. So it comes from there as well. So if we've got the inequality in one direction and the other, then that just gives us an equality. And we've shown the outer measure of A equals the outer measure of A1 plus the outer measure of A2. What was the set A1? It was, I like this version of it, A intersect the complement of this interval. And A2 was A intersect this interval. So sure enough, we've got the outer measure. Let's read the right one first. The outer measure of A intersect a set plus the outer measure of A intersect the complement of that set. This is the complement of the open interval from A to infinity. It's the closed interval from negative infinity to A, including the endpoint. That's exactly the Carey-Theodori splitting condition applied to this set here. So this set here is measurable. That is, all intervals of the form a to infinity are measurable by exercise 211. Since we're in a sigma algebra, all intervals then are in that sigma algebra. That is, all intervals are measurable. We bounce back and forth in how we've dealt with this algebra, sigma algebra stuff. Once we showed we had an algebra or a sigma algebra, then if I could demonstrate some kind of little function, some kind of little set of real numbers is measurable, then I know, well, all sets like that are in the sigma algebra. If that tells me something, that's useful. That does tell me something in this case. Before we read the next little sentence, what do you know is measurable? Sets of outer measure 0 and their complements. Oh, and intervals now. Now we know intervals are measurable. In particular, open intervals are measurable. So we've got a sigma algebra that contains all open intervals. What's an open set of real numbers look like? A countable disjoint union of open intervals. So if we've got the open intervals and we've got countable unions, then this sigma algebra must include all open sets. What was the smallest sigma algebra including the open sets? Those were called the Borel sets. So we just got a bunch of stuff, because I'd dare any of us to come up with a set that's not a Borel set. There's lots of them, but coming up with them is no minor feat. So the measurable sets includes all of the Borel sets. And honestly, I don't think any of us are going to think of a set that ain't a Borel set. So we just took a giant leap. Simply by showing intervals, we're in the sigma algebra, ultimately gives us that all Borel sets are. Can you tell me what a Borel set looks like? Let's review briefly. Gee, in section 1.4, we talked about F sigma sets and G delta sets, and F sigma delta sets and G delta sigma sets. I can tell you what those look like in a really clunky way. And those chains of sets didn't even include all the Borel sets we said. But it includes any set I could possibly think of. I'll give you that. So having the Borel sets included is a very useful thing. We have shown that outer measure is translation invariant, but what we haven't shown is the translate of a measurable set is measurable. That is, if set A satisfies the Carey-Theodori splitting condition, and we translate it, say to A plus Y, then A plus Y also satisfies the Carey-Theodori splitting condition. Now, it isn't a surprise that that occurs, but let's run through the proof. To complete this section, the translate of a measurable set is measurable. So start with E, a measurable set, Y, a real number, and A, an arbitrary set of real numbers. Then we have the following. We know the outer measure of A is the outer measure of A minus Y. That's the translation invariance of outer measure. So no problem there. We know set E is measurable. So what we're going to do is say, if I take this set, A minus Y, not just A itself, A minus Y, and I intersect it with E, and I intersect it with E complement, put the outer measures on there, we get that summation. That's the Carey-Theodori splitting condition applied to set E. See, there's an E and an E complement, with the arbitrary set of real numbers not simply being A, but being the set A minus Y. I can use any set I want to. I know E is measurable. That means for all subsets of the real numbers, blah, 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 the splitting condition holds. I'm going to claim the outer measure of this set equals the outer measure of that set, and similarly over here, and state it as a set equality, and then try to talk you into it. Well, all we're going to do now is let's translate this set by an amount y. So add y to this part and this part. That's how it would interact with the intersection. Add y to a minus y to get the set A. Add y to e to get the set e plus y. Quite plausible. Over here, similar, it's got a complement that makes it a tiny bit more involved. Add y to both of these. So a minus y translated by positive y gives you set A. E complement translated by positive number y gives you e plus y complement. You might argue, well, it gives you e complement plus y. Is that the same as this? Yeah, it's the same as that. So a little bit to be shown there, but I'm claiming that we've got equality when we do this translation. Take this set, add y to it, get that set. Similarly here, so we're translating these two sets and drawing a conclusion of equality. Yeah, because we've got translation invariance of outer measure. So this being a translate of that, these two have the same measure, same thing over here. And what we got from beginning to end is the outer measure of A equals the outer measure of e plus y plus the outer measure of A intersect e plus y complement. That means this set and the set with a complement on it, satisfying this equation for arbitrary set of real numbers A. That set satisfies the splitting condition. That's a measurable set. So translations of measurable sets are measurable, and their measures satisfy the properties they should. We've got translation invariance. So here's everything we have. A quick synopsis with an eye towards the 4 properties on our wish list of properties for a measure. So considering outer measure on a sigma algebra of measurable sets, calligraphy M, we have for any interval, the outer measure is its length, and intervals are in that sigma algebra. M star is translation invariant, and anything that's in this sigma algebra, a translation of it is also in this sigma algebra. That's what we just showed. M star is countably additive on calligraphy M. That was the thing we borrowed from section 2.5. Proposition 2.13 tells us that we've got countable additivity on this collection of measurable sets. So 1, 2, and 3, excellent. That's what we wanted. Part 4, this is not what we wanted. We wanted outer measure to be defined. Well, we wanted our measure, I should say. We wanted our measure to be defined on the power set of the reals. The measure we're going to use is only going to be defined on calligraphy M. If we stuck with outer measure, we've got property 4. We've got that we've something that's defined on the power set of the reals. Yeah, but it ain't countably additive to be shown in the future. So what we're going to do is take outer measure and restrict it to the sigma algebra of Lebesgue measurable sets. That won't equal the power set of the reals. Give me a couple of sections and we'll establish that there is a set that's not in calligraphy M. And what we will do is define Lebesgue measure to be outer measure applied to calligraphy M. So that's what Lebesgue measure is. It's the same as outer measure, except outer measure is defined on any set of real numbers, and that causes some problems. And Lebesgue measure is only defined on calligraphy M. So your problem with Lebesgue measure, it's not defined on all sets of real numbers, but it's well behaved. Your problem with outer measure is it's not well behaved. It's defined everywhere, but it's not well behaved enough for us to develop integration using only outer measure. And that takes care of the sigma algebra of measurable sets, Lebesgue measurable sets. We'll look at some properties and do a little bit more measure stuff. We've got a lot of measure stuff under our belt now. And then I think it's the next chapter, chapter 3, chapter 4, we'll use this measure theory stuff to go through and develop Lebesgue integration. So have a nice day. I will see you soon in section 2.5.